This lecture is the second lecture on first order responses. Here we're going to focus on what is called a step response. So first we'll revisit what we did in the first video, which is modelling assumptions. A first order system with constant coefficients takes a standard form. So without loss of generality, we're going to write this in time constant form. And you can see this means that we've got a t dy dt plus y of t equals k u of t. And the key coefficients we're interested in are the time constant t and the gain k. In this particular video, we want to look at the behaviour of y of t for positive time when u of t is a step and for a zero initial condition. And in particular, we want to look at how this behaviour might change as we change the coefficients t and the coefficient k. Now before we start that, let's ask ourselves, what is a step response? What are we talking about in engineering terms? And it's a bit like saying, how does the system behave when we do something with the input? But clearly here we've got a very specific type of input, that is a step input. So what's an example? We could have, what happens to the speed of a car if you suddenly depress the accelerator, that is move it from one position to another position? What happens to the temperature in a house if you suddenly turn the heating on? So that's like having a step in the heating. 1 minute it's off, next minute it's on. What happens to the voltage and the current in a resistor capacitor circuit if you suddenly turn the voltage on and before the voltage was off? Or what happens to the level of water in a tank or a bath if you suddenly turn the tap on, whereas before it was off? Now, in all these cases, we're looking at what's defined as a step response. What happens to the output when the input undergoes a step change, and here we're assuming zero initial conditions. So first you might want to see, well, what's a step actually look like? Well, a step is defined as being zero in negative time and having a fixed value in positive time, t greater than or equal to 0. A unit step has a value of 1 in positive time. So here we've plotted a unit step for you. So what you can see is here in negative time, the value is 0. Whereas in positive time, the value is 1. Now, it's quite useful to take the Laplace transform of this signal, because often we will do analysis using Laplace transforms, and although I'm not going to derive it, we've put the answer down here for you. The Laplace transform of a step is 1 over s. Now, in general, a step can have any magnitude. It may not be a unit step, and so if you have a step, for instance, of magnitude 5, then the Laplace transform would be 5 over s. So what we need to do next is actually ask, what happens to our differential equation when we make the input a unit step? And this is called the step response. And we're going to use Laplace transforms to pursue this. So given u of t is a unit step, what I can do, I can take my original differential equation, there it is, t dx dt plus x equals ku, and I want to find the Laplace transform of x of t, which I'm writing as x of s, and I'm going to define u of s equals 1 over s. Now, this was done in the first video, so I've done it slightly quicker. When you take the Laplace transform of dx dt, you get sx. And therefore, when you take the Laplace transform on the left-hand side of your model, you get this term here, s capital T plus 1 times x of s. And on the right-hand side, we had ku, so that becomes k over s, because the Laplace of u of s was 1 over s. And note, we've assumed that x of 0 equals 0. I can now rearrange this expression to find x on its own, and you will get this here. X of s is capital K over t all over s times s plus 1 over t. So the next thing is to do an inverse Laplace. Now, there are lots of videos on inverse Laplace, so we're going to do this very quickly, and we advise you look at those other videos if you need to learn how to do inverse Laplace. So in general, I've got a denominator here which has got two simple factors, an s and an s plus 1 over t. So I can do the partial fractions, and I end up with some residue, c1 over s, and some other residue c2 over s plus 1 over t. Now, without going through all the details, I can show that residue c1 is in fact k, and residue c2 is minus k, so the partial fractions for x of s are capital K over s minus capital K over s plus 1 over t. So again, if that's too fast for you, I recommend you look at the inverse Laplace videos and then learn how to do this. Next step is to do the inverse Laplace. Well, the inverse Laplace of k over s is just k, because 1 over s is a step, then k over s is a step of magnitude k. The inverse Laplace of k over s plus 1 over t is e to the minus little t over capital T. So we end up with x of t is capital K times 1 minus e to the minus t over t. So you'll notice the step response has a very simple structure. And the other thing we can do is if I put in time equals 0, you'll see I get k into 1 minus 1, which clearly gives me 0, which is what I expected. The initial condition was 0, whereas the limit as t goes to infinity of x of t is clearly going to be just k, because the e to the minus t over capital T will go to 0. So I've got two simple observations. The system starts from 0 and it finishes at capital K. Right, what we've got now is numerical example, where we can pursue this. Look at the following ODE: 0.2 dx dt plus 0.4 x equals 1. And we want to solve for this. The first thing to do is to put the system in time constant form. So that's what I've done here, and you'll notice I've got t equals 0.5 and k equals 2.5. And therefore, given that we had the solution, and I'll write it down here at the bottom in case you've forgotten it, it was k 1 minus e to the minus t over capital T. So you'll see what I've done here at the bottom is I've simply substituted in my two numbers. Capital T was 0.5, so time over capital T, in fact, is 2t. So that's why I've got a 1 minus e to the minus 2t, and k was 2.5, so that's appeared outside the brackets. So there we are. Now, what that tells us is the steady state value will be 2.5, and the time constant is 0.5. So here's a plot to illustrate what's going on, and you'll notice this value here, where it settles, is 2.5. Now, if you remember video 1, which I hope you've looked at just recently, you'll see the scale down on the bottom has been written deliberately in terms of time constants. I've got 0.5, which is capital T, 1, which is 2 capital T, 1.5, which is 3 capital T, and so on. So now, what I'm going to do is evaluate x of t at 1 time constant, 2 time constant, and so on. So here we go. X of 0, I get 2.5 times 1 minus 1, which is 0. So let's mark that. There's my start point, 0. Next, what I'm going to do is calculate x at the first time constant. So x of 0.5 equals 2.5 times 1 minus e to the minus 1. And here we go. That gives me this point here. I'm not going to calculate it quite yet. That will come on the next slide. Next, I can do x of 1 equals 2.5 times 1 minus e to the minus 2. That gives me the point marked here. And finally, x of 1.5 gives me the point here. Now, in this particular slide, all we're doing is showing the graph and giving an indication of some of the numbers. We will analyze these numbers in more detail next. So here we go. The key numbers that came up in the equation were 1 minus e to the minus 1, 1 minus e to the minus 2, 1 minus e to the minus 3, and 1 minus e to the minus 4. And you may remember, if you've looked at video 1, that e to the minus 1, e to the minus 2, e to the minus 3, e to the minus 4, these were key numbers that we recommended you remember. And we'll give a similar expectation for 1 minus e to the minus 1. So there we go, it comes out as 0.63. 1 minus e to the minus 2, 0.84. 1 minus e to the minus 3, 0.95, 1 minus e to the minus 4, 0.98. So if you look in the graph here, you'll see that we've marked the points again, but clearly the value that you'll be noticing is that after t seconds you are within 37% of the target, because if I mark it down below with another double arrow, you've moved 63% of the way. Okay, so the 37% that you saw in the previous video has appeared again here, but in a different position. So, summary of observations. If you put the model in a standard time constant form and assume that the input u of t is a step of magnitude a, so there we go, there's my time constant form, and there's my input, then what you will get is that x of t equals k, capital A, times 1 minus e to the minus t over t. So this tells you that the response follows an exponential decay from the initial value of 0 to the final value of ka, and it tells you that timescale is determined by t, so the points are 0, 0, t, 0.63 ka, 2t, 0.84 ka, 3t, 0.95 ka. So if we remember these values, hereafter plotting the responses becomes straightforward. So the key thing is the response is invariant in terms of a timescale marked with multiples of t. So first mark the time axis as 0, t, 2t, 3t, 4t, and so on. Use the coordinate pairs, and you'll probably remember these values very quickly, so we've put them down here again. So you've got 0, 0, t 0.63 ka, 2t 0.84 ka, 3t 0.95 ka, and so on. Modify the time axis by placing in the actual values of capital T, to capital T, and so on. What we'll do is we'll illustrate this process using a simple example on the next slide, and you will quickly realize how straightforward it is. So here's our example. We want to sketch the response for 6 dx dt plus 4x equals 3 with an initial condition x of 0 equals 0. So first I'm going to put it into time constant form. So we did this on the previous video, but in case you forgot, we divide by the 4, so we get 6 over 4 times dx dt plus x equals 3 over 4. So that gives me t equals 1.5 and a k equals 0.75. We can compute the steady state. Well, in this case it's already done because we can see the right hand side is 0.75, so I'm just going to write it straight down, 0.75. Finally, we compute the values of x of t, x of 2t, and so on. So what I'm going to get is that x of t equals 0.63 times 0.75. X of 2t equals 0.84 times 0.75. X of 3t equals 0.95 times 0.75, and so on. So finally, we add these points to the sketch. Right, so here we go. Let's add our sketch. We'll draw some axes down there. We mark the points t, 2t, 3t, 4t. We mark the steady state, which was 0.75, so I put that across like that, and essentially t was 63% of the way there. So I didn't calculate this exactly, but essentially what you've got there is that point, which is 0.63 times 0.75. And then you've got this point here, which was 0.84 times 0.75, and this point here, which was 0.95 times 0.75. So I can now draw a sketch like that. Now, there's an interesting observation. If it's so straightforward to go from the time constant and the gain to the sketch, well, perhaps it should be equally straightforward to go from a sketch to find the time constant and the gain. So in other words, going backwards. So what we want to do is go from the response to the parameters, and this will be quite common because in real life you'll have an engineering problem and you will be able to see the step response, but you might not know the parameters, so you can say, right, I've got the step response, let's work out what the parameters were. Now, the gain k is the ratio of the steady state output to the steady state input. And the time constant is the time taken to move from 0 to 63% of the steady state. So here we go. Here's a plot, and what we're saying is, can we estimate the parameters of the underlying? I'll write down what the model is. The model is of the form t x dot plus x equals ku, and we're interested in estimating what is t and what is capital K, and we'll assume in this particular case that the input is a unit step. So clearly the steady state is 2.5. You can see that marked here, and therefore K is 2.5. You can also see that the 63% point is marked very clearly with this purple line, and that occurs, if we follow the line down, at the time 0.5 seconds. There we go. So that tells you that the time constant, capital T, is 0.5. So there's our differential equation. 0.5 dy dt plus y of t equals 2.5 u of t. What about this example here? Well, we'll do the same thing again. If we look at the steady state, and it's roughly here, you'll see the steady state is approximately 0.8. So that's going to give me k equals 0.8. Now the next step is a bit more tricky. You need to be careful here. There's a sting in the tail of this example. If we look at the total distance moved, there it is, the total distance moved, you'll see it's 1.5 plus 0.8, which equals 2.3. So this had an initial condition which wasn't 0. And so if you want to find the time constant, you need to find the time where it's moved 63% of 2.3. Okay, so remember, in one time constant it moves 63% of from where it started to where it finishes, and the total distance moved in this case is 2.3. So if I do that quick computation, okay, 0.63 times 2.3 equals 1.45. And so we now ask ourselves, where is it moved 1.45? Well, given it starts at minus 1.5, this takes you up to x of t equals minus 0.05. So you add 1.45 to minus 1.5, and you get minus 0.05. And so you will see this is about here. So if I take this down, this gives you the value of t, so t is approximately 0.7. I can't really be any more precise than that because I'm estimating from a sketch, and that's why I'm going to use approximation. So your final equation therefore is 0.7 x dot plus x equals 0.8 u.